Hello, everyone, and thank you for joining us for today's webinar, presented by Manure Manager Magazine and sponsored by VTI. My name is Stephanie Crowley, and I'm the Editorial Director of Manure Manager. I'm joined today by Kapil Arora, Field Agricultural Engineer at Iowa State University Extension and Outreach, and Daniel Anderson, Associate Professor at Iowa State University. During today's 60-minute session, Kapil and Daniel will discuss liquid manure application uniformity and will review equipment options and their performance for uniformity across the toolbar to help you understand how well distribution works and how to make an informed decision while striving to capture all that manure has to offer. After their presentation, we'll continue through to the question and answer portion of the webinar. Should you have questions throughout the presentation, please type them into the questions tab found on your GoToWebinar control panel. Kapil and Daniel will answer these and any other questions that come up through the webinar at the end of the presentation. I'd like to thank VTI for sponsoring this webinar. VTI, or Vertical Till Injector, was founded by Phil and Rhonda Reed in 2010. Phil has more than 40 years of experience in the practice of liquid manure application. He initially designed the units for the no-till farmer in mind, but they have since expanded to cover any range of gallons and soils, from the low-volume finished manure to the high-volume dairy and sow operation needs. Some of the key features of the VTI unit are its ability to operate at high speeds with minimal soil disturbance and high residue with low draft for true manure injection. VTI can customize just about any configuration to fit toolbars and row units on brands of liquid tankers and drag hose systems, and can help customers troubleshoot any problem anytime. A network of full-service dealers all across North America ensures that parts and service are never far away. Remember, innovation, not imitation. VTI is the original true liquid manure injection system. Before we get started, I'd like to remind everyone that this webinar is being recorded and will be made available to all attendees and registrants approximately 24 hours after our live broadcast. We will also include links to the publications referenced in this presentation for you to download at your leisure. Without further ado, I will turn this over to Kapil and Daniel.
Well, thank you, Stephanie. As everybody is signing on, welcome to this webinar. My name is Kapil Arora. I'm a field agricultural engineer at Iowa State University in the Department of Extension and Outreach. Today, we are going to be talking about liquid manure distribution and application uniformity. Our presentation is set out. We'll go through introduction. We'll share what our problem is. Then we'll briefly talk about how do you verify a manifold distribution. We have tested a few manifolds and we'll share the results from those manifold testings that we have done. And then Dr. Dan Anderson will be on the program here and he'll be talking about the uniformity of liquid manure, and then we'll share our conclusions and we'll take questions after that. So to get on starting with the liquid manure application, we drew up a little schematic to share with you guys. In majority of systems these days where we are using the applicator information in our onboard controller, which couples in the GPS information with it. It decides what application rate we are using. That information gets passed on to the flow meter and the actuator, which are then controlling the manure getting pumped from the manure tank and passing it on to the distribution manifold. So this all happens in the hydraulic flow of manure before it actually gets to the distribution manifold at the end. Just to give an idea, when we are applying manure out in the field, especially liquid manure, we typically carry it in a manure tank, and we have a pump that runs that manure back to the toolbar. To get the manure out to each of the points on the toolbar, we typically use this manifold. So the onboard controller and the GPS information, which includes the drive speed, basically decides how much liquid manure in gallons per minute will flow out to the manifold. But then from the manifold out to the toolbar points, this manifold is basically responsible for distributing liquid manure out to each point that is on the toolbar. So this schematic just shows how those outlets may be laid out and manure getting out to the different points on the toolbar. We have typically in the past done area volume calibrations. These calibrations basically calibrate what the expected or approximate flow rate is through the manifold. It actually basically does volume calculations over a known area. So we typically end up with confirming if we are putting on 4,000 gallons per acre, or if we are putting on 6,000 gallons per acre. We can typically measure how much liquid we have by either weighing it or by using a flow meter, and then we go out and measure the area that we have covered. We have publication A3601 through Iowa State University. This publication does provide a detailed step-by-step procedure on how to go about doing the area volume calibration. This calibration gets you your application rate in gallons per acre or liters per hectare over the area that you are applying. But the question always comes up, does it actually address the variability across the toolbar? Is each point on the toolbar getting the same amount of manure out into the row that it is applying, or is it just an average application rate across the field? The answer is area volume calibration basically gives us an average application across the field. It is by no means a measurement on how well the manure is getting distributed across the toolbar points. Here's a quick photograph of how different points may be performing differently. We can have more liquid coming to certain points, whereas not enough liquid or maybe no liquid coming out to the other points. In this case, we will still be getting the application rate of, let's say, 4,000 gallons per acre being applied, and we'll still be okay because we can count on how many total loads we were needing to apply to a certain field, and we got that many loads applied. But from each row to the next row, the amount of liquid that gets applied is variable. So what does this problem show up, or what is the reason behind this thing being something that we need to address? It leads to erosion in confidence on part of the producer. If we have poor distribution, as you just saw in this picture, and if you can visualize in your mind, certain rows are getting too much fertilizer value put on it, while other rows do not have enough at all. So in the production of the crop itself, as we go through the growing season, the plants that are deficient in nutrients will start showing that they cannot produce as much. So we do see sometimes streaking happen because of it. You'll see yellowing of the corn or other crop which is trying to use the nutrient which is not there. So it becomes a little bit prudent on our part that we make sure that we have good distribution across the manifold. The other problems that have started to show up in the recent years is our application rates may be getting low as well. Why are we having low application rates, or why are we in this domain of operating our manifolds? Here in the upper Midwest, in Iowa and surrounding states in the Corn Belt, we are getting into split application situations where the manure that is needed for the next crop is applied in split applications. We may be applying half in fall or half in spring. Then the next reason is manure application to soybeans. In certain states, manure application is still allowed to soybeans because they can utilize it. but the amount of total nutrients that can be put on to soybeans are limited. In Iowa, I know it's only 100 pounds of available nitrogen that can be applied, so that does reduce the application rate. The third one is we are getting maybe some of our manures are starting to test really high. Some of our finishing swine manures may be getting into real high numbers on what is the total nitrogen for every 1,000 gallons or total nitrogen every 1,000 liters. And then the fourth reason is we have also switched on calculating what is the total amount of nitrogen needed for application for the upcoming crop year. So we typically were using the yield goal methodology, but now we are switching over to the maximum return to nitrogen rate calculator, and that's the MRTN calculator, and we'll briefly visit about it. So I wanted to share with you here just a analysis on nitrogen. This is total nitrogen registering at 76 pounds per 1,000 gallons. This is liquid swine manure from a finishing barn. If we take that analytical analysis and let's just say it's 70 pounds for 1,000 gallons for easy figuring, then if we are to use that number to calculate how much we can apply for our upcoming crop year, and we add to that the new method of calculating the total nitrogen need, which is MRTN. I used a price ratio index in the MRTN as 0.08, and it gave me a calculation of only 141 pounds per acre of nitrogen needed. So at that amount of nitrogen, the application rate for manure would only be about 2,000 gallons per acre. So that does bring us down into some real low numbers on application rates. The MRTN, I just wanted to bring this up, also allows that we can apply nitrogen within 10% variability. So I'm using that same number to say if we can be within that 10% variability on our manure distribution as we go across the toolbar for different points. So looking at a toolbar, this particular one is showing you different hoses, and the discharge from those hoses is directed down into the drums. We can actually measure what is the total amount of volume over a given time period that is discharged by measuring the amount collected in those drums. And from there, we can actually calculate what is the variability across each of those points. If it was 100% uniform, there was no variability at all, then the amount of liquid that is collected in each of those drums would be almost or exactly the same. That's actually not the case. In field conditions, things vary and they are not the same. So testing this thing out is relatively easy. We can do different things. To start out with, we also looked at some of the research that had been done in the past, but we didn't find anything on liquid manure manifolds. We did find some information on dry manure spreader distribution, but nothing for liquid manifolds. So we took this project on. It was partially funded by the National Pork Board, and it was a collaborative effort between several industry partners. As a part of this project, we tested out 7 tank-mounted manifolds, and we tested out 3 dragline manifolds. And the range of outlets on these manifolds were between 7 to 24. As you saw in this picture, the testing was conducted with multiple folks at the same time. So we started our clock when we started discharging into the drums, and then we forced the discharge to be outside the drums, and simultaneously we stopped our clock. So we had our given time period, and we measured over that time period how much liquid was collected. As you can also see, we are just using water in our testing. Uh, that was one of the things we ended up having to use. Folks have asked us, why didn't you use actual swine manure? And everybody who was involved in testing basically said they wouldn't be helping me with the project and getting it done if we were really playing around in manure. So we ended up using water as our fluid for conducting these tests. And we did these tests over almost a couple of years time period. And we also tested each different manifold that we could come across, especially if it had a different configuration. Also, if it had a different inlet size and location, also based on what the chamber size was, and outlet size, location, and number also differed. So all these characteristics of the manifold can lead us to different performance capabilities. So I do want to point it out that as you see the results of different testing that we have done, don't assume that the manifold is no good. It's just that it has its own performance capabilities. So some of the manifolds are suited for lower application rates, while others may be suited for higher application rates. So the first one we tested, this is in a crescent moon shape. The manure actually comes into this manifold on the top from the side, and the outlet, there are 7 outlets on a crescent moon shape. And in this particular case, as we tested it at higher application rates, we had lower variability. But then as we reduced the application rate down towards 2,000 or 1,000 gallons per acre, our variability in this setup went up. The 3 different bars that you are seeing on this graph, the black line is 0% slope, the blue line is the toolbar and the manifold are tilted at a 3% slope, and then the orange line that you are seeing there, or the orange bar that you are seeing, the toolbar and the manifold are tilted at a 6% slope. So when we were running these tests, we wanted to see if slope made a difference on how the performance and variation showed up. So on the left-hand side on the bars or on the graph itself, it's the coefficient of variation that's calculated by basically calculating the statistical analysis of coefficient of variance. You also see a red line there at 10% variability. That is the same 10% number that we were talking about earlier, coming from the maximum return to nitrogen calculation rate. So just shooting as a target if we can bring that number any lower. Now, since we have done this test, I know the manufacturer of this particular brand has probably done some modifications as well, and we haven't been back with them to test the new version of it, but just wanted to point that out, that this was done prior to them making any modifications to it. The next manifold we tested, this one had a bottom feed to it where the manure came into the chamber from the bottom up. Then the manifold had 12 outlets on the circumference of a round chamber. And then it also has the rotating bars in the center of the chamber, so that as the application rate got a little lower, some of the outlets were blocked up in discharge, and as the rotator spun around in the chamber, it would be discharging intermittently. So in this particular case, as you can see, from 1,000 gallons all the way up to 6,000 gallons, that we tested, and also on all three slopes, other than for the 2,000 gallons per acre rate, we were pretty close and pretty much within the range of that 10% variability across all slope settings in our testing. The next particular one that we tested is similar to the one that you just saw, but in this case, it only had 8 outlets. It did not have all 12 on the circumference. So it's exactly a similar model manifold, but only has 8 outlets facing towards the toolbar and not on the other side that's towards the tractor. Manure enters into this manifold also from the bottom, and it has the same configuration where there are bars inside the chamber rotating that would block off certain outlets from discharging, so the discharge is pulsed into these hoses. And this particular one, from 4,000 gallons up to 6,000 gallons, got real good, and as it got higher up towards that 6,000, it actually was giving even lower variability. But down in the 2,000, 3,000 range, it had significantly higher variability in its discharge. The next one we tested out, this is a manifold where the outlets are actually inverted. The manure enters into the manifold from the bottom, it's a drum, and then the outlets are actually on top of the drum, and the manure has to rise up into these outlets and then discharge down into the tubes, and these tubes are then connected down onto the toolbar points. In this particular setting, we actually disconnected the toolbar and we had the hoses just discharge straight down into our drums. And as you can see, it gave pretty good performance across the board on all application rates. Down in that 1,000, it was a little bit higher, but overall, we had pretty good performance that it showed up as. So it did give us the low coefficient of variation for it. We tested the same manifold again, but this time we had the toolbar attached with it. We just wanted to see if it made any difference if those hoses were draped over the toolbar and then connected down into the toolbar points. So in that configuration, which is what the real configuration out in the field would be, we did get a little bit higher variability than our previous test, but still we were below or around that 10% mark, which back to us was that it had pretty good performance for distribution. And that was across the board for all three slopes that we tested. Another one we tested, in this particular case, manure entered in from the top, and then the outlets were also on the top in this particular manifold. But as you can see, on the lower application rates, it had pretty high variability, getting up to that 6,000, even 6,000 gallons per acre. We were still higher on the 10% mark, still just getting pretty close, but still high above that 10% variability red line that you can see there. This is in one of the test runs that we ran on real low application rate. This is how this particular manifold actually showed up as. In certain cases, we did get liquid come out into the drums, and in other places it did not do any distribution at all. The sixth one that we tested had coupled outlets. We tested 8 of those. Others we just coupled according to the manufacturer and instructions, and tested out how much distribution variability was, and this one tested out pretty good, below that 10% mark, and in several measurements we were even below 5% variability on this particular manifold. This particular one had 24 outlets on its circumference. This is for one of the large toolbars where you would have 24 toolbar points, and bottom feed, all outlets on the circumference. And I would say in this particular case also 2000 and higher application rate, we were doing pretty good. The manufacturer did tell us that below 2000 they would not recommend using this particular manifold, but very easily you can see on the distribution there for the entire range of application rates and slopes. The next one we tested, this one is a rectangular manifold. The manure enters into this thing from one side, and the outlets are on both sides of the rectangle. This particular one also had pretty high variability. The manufacturer did tell us that they would actually use it in higher flow application where the application rates are really above even maybe 6,000 gallons per acre. So on the lower side, we did not see the variability where we wanted to see it below that 10% mark. This particular one had 14 outlets on its circumference, again a round one, but different manufacturer, different style. It doesn't has any bars in the chamber rotating, but it just has cutting blocks inside the chamber that run. And 3000 and higher, it showed up pretty well, and below that 10% variability. Again, across all the slope points there. The last one that we have tested, this one is top fed. Manure comes in on the top side, and down in the bottom, the outlets are weighted and they are flapped, so they don't discharge completely. The flaps open up based on the flow rate. So as the flow rate goes up, the outlets are unrestricted at that point. 4,000 gallons and higher, we actually were around 5% variability on this, but even on the lower application rates, we were still around that 10% mark. So I think this one also did pretty well in getting to those lower application rates and doing manure distribution. As I pointed out earlier, so I'll visit with this again one more time, effect of hose loops. In our first test in this particular manifold where the hoses are directly draped down, and then when the hoses are kind of looped over the toolbar, does that make a difference? And in this comparison of the performance there, you can see, and I've shared these graphs already with you. Now, with those hoses draped over the toolbar, we do see some increase in variability. This particular manifold did pretty well, and overall, the results here are very acceptable below that 10% variability number. But you guys saw this picture earlier where the variability is just dramatically high. And if you pay quick attention in this picture, you'll see the discharges in the hoses where there's nothing coming out. Those hoses are actually draping down below the toolbar on the back side. So on low application rate, what really happens is there's not much pressure in the manifold chamber. So any liquid that is sitting in the hose loops itself then is a plug. If you imagine in your mind, there is no pressure in the chamber, so there is nothing pushing the liquid in the tube itself. So anything that is hanging in that loop basically does not discharge. There is nothing as a back pressure to move that fluid along. So it almost becomes a point where the point will not discharge because the fluid cannot really flow in that distribution or in that particular line from the manifold. When you also have hoses that are crimped up in the toolbar like this, these are also practically plugged up. manure will fill up right just behind these crimps, and the liquid will not flow. So sometimes if you have access hoses hanging around on the toolbar, as you lift those toolbars up to move from one field to the other, be watchful. If the hoses are crimped up, you are basically getting very poor distribution because the liquid is just not able to flow through them. Another thing that we found out during our testing was vents that get plugged up with manure. Majority of these manifolds, on the outlets, you will see that there are vents to allow for pressure equalization. When we are applying manure in fall, sometimes we are dealing with very cold conditions when we get done with manure application. We get done in the season and we just go and park our equipment. Next fall, when we start out, or the next application routine when we start out, we need to watch for these vents. If they are plugged up, they will not allow the discharges to the hoses to discharge equally. This can lead to quite a bit of variability across the toolbar. Several times when we were testing our manifolds, we had to stop and actually go back and clean these vents out before we could run our tests. So that's a caution I want to put out for everybody to be watchful of. In certain cases, folks have actually even taken the outlets and rerouted them back into the drum. Some folks have just taken the pressure plugs off of these vents. If you take all the restrainers off of these vents, then these vents will just gargle, and they'll throw some manure out of them once in a while. So the back end of your tank may look really dirty there right around the manifold. So some folks have come up with the option of rerouting those vents back into the tank itself. Another thing I wanted to quickly touch base on is the effect of the slope. We did test these manifolds at different slopes, so I do want to bring that up. If you are on a slope, if you go and you have really wide toolbars, the thing to watch for is on the far end, on the upslope side, the hoses that are above the far toolbar point, sometimes you can see them even, they are actually going against the gravity. So the manifold, in the situation where it is applying only 2,000, 3,000 gallons per acre and is not fully pressurized, in these cases, the liquid in the manifold will tend to drift towards the downslope side, and your upslope side, especially if you have to push up against gravity, those hoses may not discharge because the elevation difference there is just prohibiting the liquid to flow uphill. So that is something to watch for in these cases. Uh, so where is the manifold in relation to the outlets, and how are those hoses laid out? We were able to see as we increased our slope in our tests that as the slope gets higher, the variability does increase across the toolbar. So we were able to capture that in our performance data as well. So improvements that I would suggest is mount your manifold at the highest possible location that you can, so that you maintain a down gradient towards the toolbar points. Use multiple manifolds, especially if you have extra wide toolbars, so that you can ensure equal supply from each manifold down to the toolbar points. Minimize or eliminate hose loops. They don't help. Use hose racks to make sure you again have down gradient towards the point. Remove or fix script hoses. Unplug your air vents and reroute those air vents whichever way works better for you. Another way is at low application rates, you could drive faster. That will push more flow rate through the manifold. If you are only at 6 or 8 points, you can look at going to a wider swath, maybe 12 point toolbar, with similar point spacing that could get you again more flow rate coming through the manifold. One other last thing I want to point out is, especially in the upper Midwest here, when we get done in one season and then it freezes over winter, next season when we bring those applicators out, uh, before we actually put them out in the field, it may be good to load them about halfway with water and do a test run and then make sure that all the points are discharging. So the review of the presentation of the slides that I've shown you here so far, make sure that each manifold that you are dealing with has its own capabilities and limitations. Don't just go out there and start making changes unless you understand them completely. Uh, I will also caution that we use water in our results. So if you are dealing with manures that have high viscosities, the numbers may be different. And what I have shared with you is available in our publication AE 3600. We have shared those links in the invitation, and they'll be available after the presentation here. So if you want to read more in detail, you can get those publications online. They are available free of charge. And I do want to thank National Port Board and industry partners for funding the research that we did, and also to Manure Manager for hosting us and holding this webinar today. So with that, I'm going to pass it on to Dr. Dan Anderson so he can take over and discuss the rest of it.
Thanks, Kapil. As Kapil mentioned, I'm Dr. Dan Anderson, Associate Professor at Iowa State University, and I go by Dr. Manure on Twitter. I don't quite have control yet. So I'm going to try and talk to you about just a little bit of manure economics, and we'll talk a little bit about just in general, and then I'm going to try and wrap around again at the end and talk about what that means for uniformity across the toolbar and how that's impacting our yield. There we go. So I wanted to start out with, we all know that manure has value, right? That's one of the reasons we're here, and the value tends to be increasing. Over the last 10 years, we've tended to see nutrient concentrations increasing in all our manures, but especially in deep pit swine manure, where I might see a typical test somewhere around 50, 1530 of nitrogen, phosphorus, and P2O5. And as Kapil mentioned, that leads to cases where we might want to be hitting some relatively low application rates. And at the same time, we've seen fertilizer prices tend to increase. And I think that's a good thing for us in the manure business, right? It went from us thinking about manure as something we have to manage, something we have to deal with, to something that's an asset to many of our farms, especially if we can find the right equipment choices so that farmers trust it as a fertilizer value, that they know what they're getting, they know that it's going to be there to support their crop growth, and we find ways to capture it. So if you look at where that puts us for typical values of swine manure, I have us right around $30 of nutrient value per 1,000 gallons. And I think that's a lot different than when I look back at the early 2000s in Iowa, we would be talking about $10 per 1,000 gallons. And when you think about what you're willing to invest in from an equipment standpoint to manage a resource where it's $10 per 1,000 gallons or $30 per 1,000 gallons, well, 20 extra dollars for every 1,000 gallons of manure I'm dealing with lets me have some options in terms of equipment, in terms of how far I'm moving manure, that really supports trying to get more from our manure. So as we see some of our manufacturers try and make bigger toolbars, trying to increase flow rate, trying to add sophistication to make sure that we're hitting rates correctly, or not just rates in terms of gallons, but trying to measure real-time nutrient concentrations, all these things start to make sense when you look at how our situation's changing and there's more potential value to be captured from that manure. And then I just wanted to look at the same thing with dairy manure, just because the situation's a little bit different. Dairy manure tends to have a little bit less nitrogen in it, especially available nitrogen. But when you look at it, there's still lots of nutrients there and potential value from that. So even though dairy manure, I tend to think of it as more dilute, we're still looking at $25 of potential value per 1,000 gallons. Where we're getting that potential value from changes a little bit, right? We go from a nitrogen source to more potassium phosphorus value, but that potential value is still there. And I think that's important to consider. And especially as we think about uniformity and what it means with nitrogen, we're tending to think about every year we're supplying the nitrogen for our next crop, right? So the uniformity of that nutrient, extremely important to us because we're relying on it to handle it just for us right now. When we think about phosphorus and potassium, is uniformity important? Absolutely, but there's some buffering capacity in the soil to handle some of the inaccuracies of how that nutrient is applied. So when you think about that from an equipment standpoint and what Kapil talked about, with dairy manure, we have a couple things happening, right? We tend to have a lot higher application rates. Maybe we're not putting the same challenges on equipment, and we tend to be focusing on phosphorus, potassium as where we're collecting our value from, and coming back and maybe putting some nitrogen on to supplement it. And that's going to handle some of our inconsistencies with uniformity with dairy manure that we don't always get with swine manure, right? If it is our only fertilizer source, we need to make sure that each corn plant in our field really has access to that nitrogen we're putting down with it. So there's lots of potential value in manure. When I look at what we had there, we were looking at $25 to $30 worth of potential nutrient value, and we're hoping to pay somewhere around $15 to $18 per 1,000 gallons to put it on, right? So it is a value-adding proposition if we can take advantage of it. So I think that gets us to ask questions like, where should we be putting it? How much should we put there? Timing, and is there right ways? And along with that, one of the things that I think uniformity across the toolbar goes with is minimizing uncertainty. When you're trying to capture this value, if you don't hit rate, right? If we over apply, or we're worried that for whatever reason our flow meter is giving us less than we should, under applying, or if one knife doesn't get any manure and the rest get more than they should, that leads to things like streaking in the field, right? Where some of those corn plants you can tell didn't get the nitrogen they need, and we're wondering what's wrong with manure as a fertilizer. And I think that's an enemy to our industry. It makes us question our fertility decisions. It makes us question if we really understand what's happening. And from an applicator standpoint, it makes them look at you and say, are you really managing my manure for me and helping with me with my fertility program? Or am I paying you not to be a fertilizer applicator, but are you a disposal company? And that's not what we want to be. So I just wanted to do a little manure economic calling, and I promise this will all make sense at the end. I looked up the price of a used Hool tank, penciled it out at roughly $40,000 to buy it, assumed I could use it for about 5 years, so I'm paying roughly $8,000 a year to own it. If I'm doing my own manure, right, this isn't a commercial applicator example, it's my own pigs, generate about 1.5 million gallons a year of swine manure from a finishing barn. If you're using wet dry feeders, looking like an Iowa farm, just by investing in that tank and toolbar, I've already invested half a penny of technology just to own the tank, right? Half a penny a gallon. So that's my base where I'm at. I haven't paid employees. I haven't paid for fuel. I haven't even paid for a tractor to haul that tank around. And I'm still not going to, right? My economics here are a little incomplete, but I wanted to give us a picture of where we're looking at. And if you just make some common assumptions about how long does it take to load a tank, unload it, and how quickly can I get from point A to point B, right, from my farm to my field. If you're going half a mile, we might be looking at 30 minutes of load. If we're looking at 5 miles to get there, we might be looking at something like 100 minutes of load, right? A little over an hour and a half. So the economics don't really look in our favor there, right? Moving manure from our farm gets time expensive really quickly. But if you start penciling out what that might cost, right? And let's just say labor cost is $10 an hour. I'm probably low. I work at Iowa State and I can hire students at $10 an hour, so it's what I picked. And I'm not paying any insurance on that, right? So clearly in the real world, we'll probably have to crank that number up a little bit, and a fuel cost of $15 an hour, if you start thinking about what that marginal cost is to move manure a little bit further, right? That half a mile field right next to our farm, we're looking at 2/10 of a penny, and to get 5 miles away, we're only looking at a penny, right? So does it add up? Absolutely, but when we think about capturing the value from those nutrients, there's opportunities for us there. So I looked at some total costs and what it might be costing us there for our manure, anywhere from a little less than a penny to about a penny and a half when I'm moving 5 miles away, right? And that's quite a ways away, and we can argue that the numbers aren't quite right. There's other expenses in there. But I think it's important for us to think about what those numbers really are. Does it increase? Yes. But when you look at the potential value we have and our ability to capture it, especially with good manure management practices, there's value for us to get by finding fields where we need all of those nutrients, or making sure that the nitrogen's well distributed so that we can take advantage of all those nutrients. And oftentimes we talk about phosphorus in soil, and we should be making some, especially with dairy manure, decisions based on phosphorus. I'm not going to talk through this because every state does a little bit differently, but you really want to be thinking about that as capturing value. And I have an example to sort of walk through what this means. So if we had two fields, one where the soil test is 50, right? I'm in that high zone. That phosphorus basically has no value to support crop production, but that field is close, compared to a field where it's a ways away, but I need that phosphorus to support crop production. What does that mean for what my manure is actually worth? And if I start doing that and subtracting off what I think my application expenses are, in field A, that manure, since I didn't need the P, I'm only getting value from the nitrogen and the phosphorus, or in the potassium. I had $23 worth of potential value to start with. I'm paying about $7 per thousand to get it applied. The manure offers me $16 worth of value, right? In field B, I'm capturing all that nutrient, I need it all. So I'm starting from a baseline of 30. And even though my application expenses are a little bit higher, that manure still offers the same value to me in my operation, right? Because I get something from all of it. So what does that mean for variability? I know this is a picture Kapila showed a lot, but I think it really illustrates just how variable some of these toolbars are. And I'm going to do the same thing, the same sort of economics problem for you when we think about it. So if you take those knives and look at some of the coefficient of variations that we had, here I'm going to pick one toolbar, right? I was aiming for an average of 150 pounds of nitrogen per acre. And based on the hydraulic variabilities and just assuming that the manure nutrients went with the water, said, what if the coefficient of variation among the points was 35%? We might have one knife where we're only getting 70 pounds of nitrogen, another where we're getting 220. And I want to compare that to a toolbar where the coefficient of variation is sort of what we said we were going to aim for, 10%, right? That's about what anhydrous toolbars are. Seems like a good number to shoot for. And there, when you look at it, we might have a low of 120 and a high of 170, right? And if you start thinking about what does that mean for corn yield and putting it in practice, all of a sudden I have a column here, and this is corn soybean rotation, best estimates I can make for Iowa conditions, corn soybean rotation. Your mileage will vary based on what state you're in, the weather conditions you have, and past fertility practices. But really, if you can go from something where you're at 35% variation to something where you're at 10% coefficient of variation, we're looking for somewhere around 4 bushels an acre of yield improvement, right? So 4 corn's roughly $3, maybe a little more. Looking at $12 an acre of potential profit from investing in a piece of technology that better suits your needs. And that may not sound like much, but start adding that up over multiple acres, multiple years, and some of these investments really start to pencil out. So with that, I know that was quick, but we're looking forward to some questions for you, discussion you might have. And my first one is for Kapil. A question I get all the time since we did this work and started working on this is, what's worse, hose loops or different sizes hose? Obviously, the points further out on the toolbar, we need to run more hose to get them. And oftentimes people have tried to run longer hoses in the middle to match hose lengths.
So if you try to match up the hose length, all you are doing there is pipe friction. So as long as you are down gradient on each one of those, the points that are shorter length hose, they'll start discharging quicker. So that's maybe a second difference or maybe a second and a half difference by the time the manure gets to the farther points which have longer hoses. So all you're doing is just in the very starting of that toolbar, you are making sure that each point is discharging evenly by having the same length hose around those manifolds. As long as they are all going down gradient and they're from the manifold higher up, you're down gradient, that should work out in your favor. If they are looping down below and you get these big loops that are doing almost a U-shaped curve off of the toolbar, then that becomes a problem, because in that U shape, which is hanging down from the toolbar, that will act as a plug and that will force your point to not discharge if there is no pressure in the manifold.
So don't worry about shorter hoses in the middle, it's okay.
Yeah, I would not say that would be a big difference. If 1 to 2 seconds on the outer points makes a difference for you, then that's something that you would worry about having the same length hoses.
Thanks so much, Kapil and Daniel, for this fantastic presentation. We do have a few questions from the audience here. If you have any more questions for Kapil and Dan, please post them in the question tab on your GoToWebinar panel. The first one is just for Kapil here. What are the typical outlet tube sizes off the manifolds, Kapil, that you studied in your research?
I think most of them were 2 inches, maybe 4 inches. Those were the most common ones that we came across. And these would be the outside diameters on those.
Okay. I hope that answers your question, Mark. Feel free to comment back in the chat box if you are looking for more information on that.
And I think the important thing to remember, the important thing to remember there is getting too small of hose, right? That's the way your plumbing system often works in your house, is try and make a smaller pipe size to make sure you have pressure to things that are further away, right? But in Manure systems, that clogs up. So while that might seem like an easy solution to try and help your uniformity, think smaller outlet sizes, at some point it leads to plugging. And in one of our tests where we were doing not water, silage runoff, on one of the manifolds, we managed to run a rock into the manifold, plug it up, and it was one with hydraulics in it where you spin it. And if you get a rock stuck in there and that stops spinning, you block the same outlet all the time. So some of these solutions still have maintenance problems, right, when you move them to the real world.
Yeah, that makes perfect sense. Absolutely. We have another question here, kind of along the same lines, I would assume, that's coming from Ted. Your tests assume the outlets, that is the application terminations, have no back pressure or restriction. Is that realistic in most injection tool configurations?
Yeah, most of the time we're cutting a cavity and it's discharging into the air, right? It's discharging into an open cavity. So really there's very little back pressure at the outlet most of the time.
Yeah, by the time you get into those low application rates, that's where we got into this question to begin with, was we don't have much back pressure from the manifold out to the toolbar point. So they are basically flowing on gravity.
Okay. Another question here from the audience. You reported in GPA. What was the standardized travel speed, or GPM, for the targeted rates?
The travel speeds that we were shooting for 5 miles per hour. That's what we use here in the upper Midwest as our standard application drive speeds, especially when you are hauling those 6,000, 8,000 gallon manure tanks out in the field. I do know a few folks are able to achieve a little bit higher rate travel speeds of about 7.5 miles per hour. So those differences can come up. But we control the gallons per minute going through the manifold in relation to the application rate of gallons per acre. So those were both calculated, so we could actually plug those numbers in to make sure that our flow was consistent during our measurements.
And as Kapil mentioned, trying to increase travel speed there is a way to help some of the manifolds get more gallons per minute and essentially improve performance, right? So if you can go from 5 miles an hour to 7.5 miles an hour, if at 5 miles an hour you assumed you were at 4,000, if you're going time and a half, that would be equivalent to looking at 6,000 on our figure, right? And it definitely did improve, and I think that's been one of the reasons you see some farms who are trying to hit low application rates moving to injectors that tend to need less draft and let you move through the field a little faster.
Yeah, that's almost 50% more flow rate through the manifold at those numbers. So, yep.
Great, thank you. Another question here. Is Iowa State University still testing manifolds for uniformity?
Yes, we are still continuing to do that. Actually, I'm talking to one more manifold manufacturer, and hopefully we'll probably be doing that yet this fall. So yes, if there are a different configuration, or if it is the same configuration we tested earlier but has gone through modifications or significant design changes, then yes, we are still continuing to do those testing.
Okay, another question here from the audience. Have you had any experience with the Harvest Lab from John Deere or other sensors to measure NPK during application?
I'll let you answer that one, Dan.
I have not personally done any testing or evaluation on it, but I do know some operators that have run it, and I've looked at some of the data they've generated from the field. If you ask a more specific question, I can probably try and address that, but it's technology that's been around a long time. It is not directly measuring nutrient concentrations. It's indirectly measuring basically some absorption characteristics of the manure at lots of different wavelengths of light, and they generate correlation coefficients that try and relate that absorption to different nutrient properties. And in some cases, if you have the right pieces of technology hooked together, it will speed you up and slow you down in the field to try and stay at a consistent application rate. If you are targeting a nutrient like nitrogen and have a good calibration curve, that might make a lot of sense. If you're doing something like phosphorus application rates, it makes probably a little bit less sense unless you're going to try and use that number to say, this is how much exact nitrogen I applied to the field and come back and supplement it. I think it is an interesting piece of equipment. Those calibration curves are getting better, but one thing to remember is that anytime we change feeding practices, there's a chance it'll change what that calibration curve should look like.
Okay, I hope that answers your question, Ghislaine. If you'd like to follow up, please add it in the chat box and I'll pose that to Dan and Kapil. A couple more questions here. Is there a difference in the bottom feed manifolds in comparison to manifolds where manure comes out on top or on the side?
So in our testing, we did see that the bottom feed manifolds gave us somewhat bit lower numbers on variability. So they did not have as much variability in comparison to the ones where manure actually came in from the top. When we get into these situations where there is no pressure, then especially when manure falls into the manifold from the top, it tends to create, it tends to create more turbulence within that chamber. And that potentially is the reason why we may be getting some variability in the discharges. So we did see somewhat more uniformity from bottom feed manifolds.
And especially, I think one manifold that we tested there, it was the crescent moon one. That manure came in sort of at an angle, right, rather than directly from the top or bottom. And on that one, we could definitely, from our test results, see that it was getting certain turbulence patterns within inside the unit that really caused some of the variability problems to occur. So dampening out the fluid inertia as you go in is important. And in some configurations, that's easier than in others.
For sure. Okay. If the manure is testing too high in nitrogen and the application rate is only 1,500 gallons per acre, should water be added to the manure to achieve more uniform application?
Yeah, so at that application rate, yeah, you're pushing your manifold for performing at those low rate, and your gallons per minute or gallons per second going through the chamber cavity will be low. Trying to increase the flow through there, as Dan pointed out, driving faster can help. Maybe going to a wider toolbar will force more gallons per minute through that manifold. And adding more liquid into the system, I would caution against it, because by doing that, even if you were to go from 1,500 gallons to 2,000 gallons per acre, that's 500 gallons more per acre. And that can add up pretty significantly on your barn, whether you are dealing with just liquid swine manure there. That can be a pretty big number on total number of gallons that you will add. So you'll end up paying for your liquid, water that you add, then you'll also end up paying for having to haul all that additional water that you added out to the field. In those cases, it may be just as easy to spend the money and look at a manifold that gives you a different performance. Maybe get back in with the supplier that you got your first manifold from and see if they have an a different manifold or a different version of it?
Yeah, so as Kapil mentioned there, if you think adding 500 gallons, let's say an acre, going from 1,500 to 2,000, if you're paying a penny and a half, 2 pennies a gallon, let's just say 2 pennies a gallon for fun to make it easy math, that means you're spending $10 more in application costs per acre. And if you could go from 35% variability to 10%, right? I estimated that was worth roughly four bushels of corn. Maybe you can get 12 out of it. So you've almost made it work for you, right? So I think looking towards that piece of equipment and really investing in a strategy where it's not something where I'm going to have a continuous cost, but I have that capital cost to make sure it's the piece that fits my farm is definitely a better way to go.
And investing in a manifold is a one-time cost, and it's going to last you at least 15 plus years. Whereas if you are adding water back into your system, you'll be adding water every year, and that will be money out of your pocket each year.
Okay, that's great. That is all the time that we have for today's webinar. So with that, I would like to extend a great big thank you again to Kapil Arora and to Daniel Anderson with Iowa State University for an extension for joining us on today's webinar. If there are any questions that we didn't get to, I will pose those to Kapil and Dan, and we'll try and get the answers to you. You can also get in touch with them directly. Kapil has provided his contact information in the chat box. And you can easily reach Dan on Twitter at Dr. Manure. That's the best place to find him there. So thank you again to both of our speakers and to our generous sponsor, VTI, for making today's presentation possible. Thank you to all of our attendees. You will be receiving a follow-up email from us within 24 hours with a recording of the presentation, as well as the links and reference materials mentioned during this webinar. Just a reminder to please visit manuremanager.com/webinars for more information about upcoming webinars. And thanks again for everyone for joining us, and have a great afternoon.